All right, I think it's time to get started. Welcome. Not interested?
Sorry, wrong class.
All right. It's not for everybody, I guess. This is Theory of Computation. I hope you're in the right place. This is a classy room, although I've never been to this building before, and it's kind of annoying to have to come all the way over here from, I've always taught in Banff, so sorry for the inconvenience, but it's a chandelier. We don't have that in Banff. So welcome to Theory of Computation. This is, mostly math majors and computer science majors. I hope that describes you, although if it doesn't, that's fine too. I'm glad you're here. Let's just go over the syllabus a little bit. I hope that you can see the screen okay. I think it's pretty good. I'm going to be writing on the screen rather than on the whiteboard because I intend to record everything that we do during class time so that you can watch it again if you want to. Anyway, this is Theory of Computation. You can see at the top of the syllabus there information about me. My name is Chris Stecker. That's how you say my last name. The email address there is probably the easiest way to get in touch with me. My office phone number is there, although nobody ever calls me. And I don't know if you would ever have any reason to call me, but you can call me at my office, I guess, if you want to. My office is Banff 16, and the office hours are listed right there. Those times always include the time right before class. And actually, I have 2 classes in this building in the afternoons. So I have another class before this one, and 30 minutes in between, which is not quite enough time to walk all the way back there and then walk back here. So probably, if you come even 30 minutes early, you will just see me sitting around here. So I would be happy to chat at those times. Otherwise, or the other times, I'm going to do all of my office hours on Zoom rather than in my office. I actually, I'm pretty sure that I gave COVID to one of my students last semester, and I don't want to do that again. So let's do all the office hours on Zoom. Although, like I said, if you come early, if you want to talk about homework or whatever, you can come 20 minutes early. I'll probably be here, but not on Wednesdays. You will notice on Wednesday classes at a different time, which is confusing, but I hope you can handle that. Our final exam is there, May 10th on Tuesday at 3 p.m., so put that in your calendar. And you will see a link to the class website, which is where you'll go if you shoot that QR code. You will want to go there often because this is where I'm going to post the homework assignments from week to week. This is also where I'm going to post links to all the videos that I do. So what I'm going to do is, during class, I'm writing this into a notability document, which I will export as a PDF. So if you go to the class website after the fact, Theory of Computation. You into it?
Yes.
Yes. All right. I had some so people showed up and left because they were in the wrong place. Each day I'm going to post the video of what we do, and also I'll post a PDF of the things that I wrote. So if you just want to refresh your memory, check out the PDF. If you really want to hear the whole thing again, you can check out the video. Also that's where you'll see the homework assignments. We have a textbook. It's called Formal Language, A Practical Introduction. I would not expect you to bring the book to class from day to day. I didn't bring mine today. And I don't see any of you brought yours today. That's fine. For the most part, you're going to want the book just for the homework problems. I'm not going to give you reading assignments out of the textbook, but that's where we're going to find all or almost all of our homework problems for the semester. Just between you and me, I don't know if you bought the book yet, but just between you and me, there is a bootleg PDF of this textbook that's fairly easy to find using Google. I would never suggest that anybody actually do that, but I'm just saying as well. All right. So let's look at the course description. You will see there. This is the official description on the books. I didn't write these words here. It says, this course explores what computers can and can't do by examining simple mathematical models of computation. Topics include finite state machines, regular expressions, non-determinism, push-down automata, context-free grammars, and Turing machines. We will see that there are limits to what computers can do, and in doing so, we will learn about what a computer really is. You may be surprised. I didn't write those words. That's the official description of the course. Although it's true, I think you may be surprised about this class. It's kind of hard to explain to people what this class is really about. It's about computation, and it's about computers, but it's not actually about any specific computer, and this is not a programming class, so we're not going to be doing specific stuff on specific computers, but it's more about the theoretical idea of computation and the concept of a computing machine, sort of in the abstract. All right. A lot of what we talk about is based on the theoretical work that was done by a mathematician named Alan Turing at the beginning of the 20th century, who is, I would say, by any measure, one of the most influential mathematicians of the 20th century. He basically created computer science as we know it. Although Turing himself did not have a computer like we have computers. And so the class is not about sort of our specific computers, but it's about the idea of computers, more like that. I'll get into more about that when we get down to it. Let's just go through the rest of the syllabus here. So it says we're going to have 2 exams during the semester, during our class time on February 25th and April 1st. So put those in your calendar. It says students will not use calculators or other electronic gadgetry during exams. There's really you would not want to use a calculator for our stuff. So let's just say no calculators. All right. We're going to have 2 midterm, 2 in-class exams are going to be weighted equally in your course rate, with the final exam weighted double. The final exam is cumulative, but the midterms will not be. That's just details. All right, so those are the tests. We also have homework. We're going to have homework assignments due each week. Did I say on here? I want them to be due. Yeah, it says on the next page there. Homework's going to be due each Wednesday night at midnight. And the assignment on Wednesday covers the previous week's material. So, we have a certain amount of material from Tuesday through Friday each week, and then that stuff will be due on homework on Wednesday of the following week. All right. This semester, we are going to do all of our assignments electronically on GradeScope. I don't know if you've used GradeScope before, but it's just it's sort of an electronic homework submission portal, if you will, just so that you don't give me your diseased papers and I don't give you my diseased papers. We're going to do everything on GradeScope. It says there, late homeworks without excuse will lose 1/3 credit for each calendar day. I hope that makes sense. The way that GradeScope works, actually, I thought maybe we could just, how about we read through the rest of the syllabus, and then I have just sort of a simple dummy assignment just to make sure that everybody understands how to do the GradeScope thing. You can probably use it in your other classes, but the idea is you write all your stuff just on hand, by hand on paper, and then you submit pictures with your phone to GradeScope of what you wrote by hand. Okay, anyway, we're going to have a quiz each week. So the homeworks, I think I skipped over this part about the homeworks. It said the students are encouraged to work together on the homework assignments. I hope that you will work together with each other. If you got friends, might as well use them, right? You can work with your friends, although I still want to see each person give me an individual submission, but it's totally fine with me if you are working together with other people. This is, in some sense, the purpose of the quizzes. So the homework's due every Wednesday, and on Friday will be the quiz. And the quiz covers the same stuff that was on the homework for the Wednesday, just 2 days earlier. And the point of the quiz is just sort of to make sure that you actually understood the homework yourself rather than copying it from your friends. So the quiz is not meant to be like a big stressful event every week. You do the homework, it's due on Wednesday. The quiz will take 10 or 15 minutes just at the beginning of class on Friday. There will be something like 1 or 2 questions that are meant to be very similar to the ones that were on the homework. So if you did the homework and you more or less understood everything fine on Wednesday, you should do fine on the quiz without any kind of extra extreme effort. That's the idea behind the quizzes. All right? It also says the quizzes no calculators on the quizzes. Again, you won't want a calculator anyway. All right. I thought it might be fun about the grading. So that's your whole grade is those three things: homework, quizzes, and exams. And just for fun, I would like you all to decide for yourselves how you want those to be weighted in your total grade. So in these three categories, you can choose percentages for how much you want the homework to be worth, the quizzes, and the tests. So it says sometime on or before February 4th. By this time, you will have seen something like 2 homework assignments and at least 1 quiz, so you'll have some idea of what the assignments are like by then. Just send me an email and tell me what percentages you want in each category. So the rules has to add up to 100, obviously. Each of the 3 categories has to be at least 30, and then you can't change your mind later. Hi. This is theory of computation. All right. So I would like you all to think about, what do you think would be sort of the best, I'm going to close the door. What do you think is the best reflection of your knowledge? What's most representative of your skills, the homework, the quizzes, and the exams? Think about it, and, in a few weeks, send me an email, let me know what you want. All right? Somehow I ran out of copies of the syllabus. Let me see if I can. I'm trying to think if I have one on my iPad. I don't really. I could go here. Nah, forget it. What else does it say? Can I just look? Online submissions, office hours. Okay, so you will see a note about the office hours. If you read that, it just says basically, I hope that you will feel comfortable talking to me outside of our normal class time. If you have extra questions about the homework, some of the homework questions are going to be a little tricky, and I hope that you would feel free to talk to me. I intend for you to be challenged, of course, by the class, and I want to help out any way that I can when that happens. There's also a note about attendance. Yeah, there's some weird noise over there on the table. I don't know what. About the attendance, you will notice attendance is not officially part of your grade, so there's no penalty for missing class. And if you have to miss class, if you're sick or whatever, I hope that it will be fairly easy to stay on track, just because I am going to be posting everything that we do during class time is going to be posted on YouTube, and you can check it out after the fact. If you do miss class, I will still expect you to stay on schedule with the homework assignments and the quizzes or whatever. So if you miss a quiz, send me an email or whatever, and we will work out how you're going to work that out. But what it says on the syllabus is basically it's your job to contact me. If you miss a homework or if you miss a quiz, I'm not going to chase after you and call your mom and say, hey, you missed a quiz. It's up to you to talk to me and make sure that we make it up. I'm not trying to be a tough guy about it. It's just it's your job. Of course, if you're sick or whatever, then we will absolutely make up the quiz or whatever it is. But it's your responsibility to initiate those discussions. All right? Excellent. So I would like to just real quick practice the GradeScope thing, because I want to make sure that everybody is able to do that. So you should have gotten an email earlier today when I created an account for you at GradeScope for this class. So your assignment for the next few minutes, I'm going to walk around and just make sure that it works for everybody. I would suggest you do this with your phone because you're going to send in pictures, and it's as far as I'm concerned, it's easiest to just do the whole thing through your phone, although you can use your computer if you want to. What I would like you to do is just write on a piece of paper something interesting about yourself. And submit it into GradeScope. I don't care what you write. If you don't want to tell me anything about yourself, that's okay too, I guess. To sign into GradeScope, you should find that email that you were sent earlier today and click a link in there or something, and sign in. So let's just take a moment. I will walk around. Please let me know if it's not working out for you. That's fine. Sure. Okay. Yeah. Yeah, you somehow saved the Okay. Perfect. So you can I've never seen that. That's much better than the exactly. Yep. Doing okay? Good. All right. I'll give us a couple more minutes and then we can get started. All right, let's get into it then. So if, I don't know if everybody is totally done, but let me know if there are problems. I just hope, you know, the GradeScope thing is a little bit of a pain sometimes, and I hope that that's not an obstacle for anybody. If you ever have problems with the GradeScope, let me know. And if you know, if it's like the homework is due and for some reason it's not working, you can always email it to me, but it's much easier for me to receive them through GradeScope. So I would prefer that. All right, let's talk about the theory of computation. So for today, I want to do like a little maybe overview of what the course is about, and then we'll get into some details if we have time. I hope you don't mind me sitting. I like this high stool here. It's hard for me to stand up and write on this thing at the same time, so I'm gonna play it like this. So, like I said, this course is kind of about the abstract idea of a computer. The idea of a computer. And this actually, as far as the mathematics that you have learned in your lifetime, this may be the course which is the most recent in history. Like, when you're a kid, the math that you learn as a kid is super old. But the stuff that we're going to be talking about is essentially all 20th century, and much of it is like mid to late 20th century, which is kind of interesting, I guess. The beginnings of this theory, you can see this from before the 20th century when some people were having similar kinds of ideas, but really it didn't go kind of mainstream until the 20th century with, like I said, the work of Turing. But I will just say, to kind of set the stage historically, around the beginning of the 20th century, people started to become interested in, people were thinking about, like for the first time in a, I'm going to try to write legibly here. For the first time, seriously thinking about algorithms. Now, the word algorithm, these days is kind of a familiar word, and it basically means a specific formalized method for doing something, or some kind of procedure which usually has to have like finitely many steps by which you can solve a problem or give an answer to a kind of question. All right, that's what an algorithm is. So maybe I'll try and say something like a definition of this word. This would be a formal process for answering a question, which could be, a mathematical question or some other kind of question, I guess, where all of the steps are described specifically, and will succeed after finitely many steps. All right, this is basically what people mean when they say algorithm. And another way to say what an algorithm is these days, you could just say, well, an algorithm is like a computer program. A computer program is an algorithm. And anything that's, if you think it might be an algorithm, the way to tell is, can you write a program that does it? And if you can, then it's an algorithm. An algorithm is not allowed to have sort of ambiguous steps. Somebody trying to get in? An algorithm is not allowed to have ambiguous steps in it. Every step has to be specifically, described specifically. I said that, described specifically. All right? That's what an algorithm is. But I'm here to tell you, this description of what an algorithm is, what I just wrote, that little sentence there, this is not a mathematical statement here, or description, not a mathematical definition of what an algorithm is. All right, because I used a lot of words in there that don't have a specific mathematical meaning. For example, a formal process for answering a question. I'll say answer, maybe steps. Steps, right? What exactly counts as a step? What exactly counts as a process? And what would constitute an answer to a question? These are all things which I didn't give you specific mathematical definitions for those terms that I'm using. Now, I don't know if it sounds like I'm just being like a picky mathematician about this, but actually, this is a serious problem that had been identified around the beginning of the 20th century. All the, big shot mathematicians in the world, or at least the, unfortunately, we tend to tell the history of mathematics through an exclusively like European centric lens, especially in the 20th century. So when I say all the top mathematical minds in the world were thinking about this problem, unfortunately, what I mean by that is like all the white male mathematicians in the world were thinking about this problem. That's true. It's not all the top mathematicians in the world. But anyway, what I'm saying is the global mathematical community was intensely focused on the question of what exactly is an algorithm. And I'll give you an example. One big problem at the time, a big question, mathematical question at the time. Come on now. big question around the beginning of the 20th century. There was actually an international meeting of mathematicians in which the guy who was essentially the top dog at the time was named David Hilbert. He was a mathematician, and he came up with a list of problems for the new century. This was in the year 1901, I think this happened. And he had a list of about 30 math problems that he had identified as the most important unsolved problems for the new 20th century. And it happened across the whole 20th century. People were intensely working on these problems. They became known as the Hilbert Problems. And one of the Hilbert Problems is this question about can we find the solutions to any, I left out a word here. Find the integer solutions to any polynomial with integer coefficients. If you have a polynomial, if you have a polynomial, you probably know, you can just use your calculator to find the roots of a polynomial. Your calculator can do that. But if you focus only on polynomials with integer coefficients, and you only are looking for integer solutions, this is much harder. The way that your calculator finds the roots of polynomials is by doing some kind of approximations using fancy numerical analysis. But if you try to do this exactly without approximating and find integer solutions, this is known as the Diophantine equations problem. Diophantine equations problem. And you can, read a Wikipedia page about this if you're interested. The Diophantine equation problem. It says, if I give you a polynomial with integer coefficients, can you find all the integer solutions? Or maybe say, there are no integer solutions for this polynomial, all right? This had been around for a long time. I'm talking about by the year 1901. This question had been around for a long time, and nobody knew how to do it, how to find the integer solutions of an integer polynomial. And in fact, people have been trying and failing to do this for so long that many people believed it was impossible to solve this problem. That is, some people started thinking, well, maybe there just is no method to find the integer solutions to an integer polynomial. Maybe there is no method, all right? So the thing to do in such a case is, well, let's try to prove mathematically that there is no method to solve those kinds of problems. This had never been done before in mathematics, to prove that a certain problem was unsolvable, or to actually write a proof that you could not prove something else. This is a little weird. But in order to do this, you need to actually know specifically, mathematically, what constitutes an algorithm, all right? If you want to prove that there is no method possible to solve this kind of problem, then you have to understand what exactly do I mean by method to solve this problem, all right? The question comes up, what counts as a method for solving the problem? If you want to prove that there can be no method, what counts? In fact, actually, it has been proven by now. There is no algorithm to solve the Diophantine equations problem. This is one of the first examples of a mathematical problem which is now known to be unsolvable. You can prove that there is no algorithm that solves this problem. But anyway, this kind of business, this requires a real definition, mathematically, a real definition of the word algorithm. Not using these kind of wishy-washy terminology like I did before about steps and answers and questions and process, whatever. You got to say, really, what counts as a step? What counts as a procedure, all right? A real definition of algorithm. If you wanted to, for example, prove there is no algorithm to solve the Diophantine equations problem, you have to say what you mean by algorithm to begin with. And many mathematicians tried to come up with ideas about how we're going to describe what an algorithm is. The one that really stuck and was extremely influential was Turing. All right, this was Turing's major contribution. Was he gave a real definition of what counts as an algorithm. And It's a definition which to us today I think seems very ordinary, but at the time was really kind of a revolution. So Turing, he lived 1912 to 1950. I wrote this down before, 54, all right? And he basically did everything which I'm about to describe. He basically wrote in one mathematics article, which has been described as the most influential single article in the history of mathematics. You could say it sort of changed the course of the 20th century. Although it was kind of inevitable. I think if Turing hadn't done it, somebody else would have done it. And other people were close to doing it anyway. But anyway, Turing decided an algorithm, this is the definition that he came up with for an algorithm, is any computation. Really what I mean by that is just any function where you plug something into it and you get some answer out of it, all right? Anyway, any computation which can, in theory, be performed by a machine. Turing had this idea that in order for something to really count as a mathematical process with unambiguous steps, what that means is it's something that you could build a machine to do it for you. If you're doing this by like turning a crank on some machine, then obviously that machine is not, it is doing unambiguous things. It's not making its own decisions from step to step. And certainly it is doing things for a finite amount of time, and then it stops after a while, all right? This is Turing's big idea. An algorithm is any procedure which could, in theory, be mechanized, right? Turned into a computation on a machine. And furthermore, now this is still not real specific mathematical terminology that I'm using here, but Turing described mathematically the precise, I'll say the exact capabilities of the machine that he had in mind. The exact capabilities of the machine to be used. All right? And he described this in complete mathematical mumbo jumbo that we will eventually get to in this semester. All right. This is what really sort of sealed the deal. He said an algorithm is any procedure that you can compute using this machine, and then he described exactly what that machine would look like very specifically, what kinds of things, what kinds of steps it can do, and this was not a hugely, I don't know, this doesn't sound like such a revolutionary idea, but it really was. At the time, the beginning of the 20th century, computing machines did exist in the real world. Calculating machines. I actually have a personal interest in antique calculating machines. There were like mechanical adding machines that, you know, had like metal boxes full of gears that looked like typewriters that could do adding and multiplying. So the world, you know, there existed in the world computing machines at that time, but they were, for the most part, sort of purpose-built machines. Like, here's a machine for adding. Here's a machine that can multiply. Turing's idea, though, that was he defined one specific machine. He described it. He called it his machine that he described in this paper. He called it the universal machine. And this was kind of the revolutionary idea that was not, this concept didn't really exist in the public mind the way that everybody knows about the universal machine today. But Turing's big idea was, I'm talking about machines that compute, but I'm not talking about a machine built for adding or a machine built for multiplying. I'm talking about a single machine which in theory could do anything, which you could rearrange, reconfigure the machine to do whatever you want, all right? This, of course, is what a computer is today. Like, a computer is a machine that can do anything. That's the whole point of the computer. And sometimes I wonder, like, if you met somebody from, you know, 500 years ago who went into the future, like to our present day, someone from the past, and you said, yeah, the world is totally different now because we have computers, they would say, what does a computer do? What is it for? I think the only sensible answer is, well, it does everything. Like, it can do whatever you want it to do. That's what's useful, that's what's good about it. It's not just an adding machine, it's not just a calculator, but I mean, provided that you have the patience to write code for it, the computer does everything. That's the point of it. So Turing had this idea that there could be one machine to rule them all. He called it the universal machine. Nowadays, this is referred to as the Turing machine, this particular mathematical description of Turing's machine. Now, in his lifetime, Turing never saw a universal machine actually built in the real world. Like, the technology was not there. And Turing didn't build one himself. He built a lot of machines. Actually, Turing is like one of the great heroes of World War II. He built some, not universal machines, but specific purpose-built machines to crack the Nazi encryption codes that were used during World War II. And it's hard to speculate, but it's been said that Alan Turing, as an individual person, certainly more than any soldier on the battlefield, Alan Turing, as an individual, was responsible for saving more lives during World War II than any other individual person because of the work that he did on the Enigma machine, which was the Nazi code machine. Anyway, this is Turing's great accomplishment, and I mean his great idea, and I would say a huge part of the scientific and mathematical endeavor of the entire 20th century was focused on realizing Turing's idea. Everybody said, oh, okay, we can make a universal machine. Let's spend 100% of our efforts for the next 5 decades to actually build universal machines. And now everybody walks around with a universal machine in their pocket. It's all, that whole thing was sort of like jump-started by Turing's basic idea. Like I said, somebody else would have had the idea if he hadn't had it, but this is, that's why they say this was one of the most influential individual ideas ever. Certainly extremely influential in the 20th century. All right. Okay, so what we're going to talk about in this class, so we will discuss, specifically we are going to talk about Turing's universal machine, but we're going to discuss other sort of related topics. And in fact, just because of the way the course is organized, we're not actually going to get to the universal machine until towards the end of the semester. But we will discuss what kinds of things can be computed by a universal machine. I just said the point of the universal machine is that it can do everything. But actually, it can't do everything, because I also said it has now been proven that there is no algorithm to solve the Diophantine equations problem. So it's a fact. You cannot solve Diophantine equations using a computer. It's true. Using a universal machine, which is a computer. What kinds of things can I just say, Turing machine compute? I think the surprising answer is not everything. Even though, if I'm just speaking casually, I would say the whole point of a computer is that it can do anything. But if you think about it, really, you should ask me, really anything? You really mean anything? The computer can do anything? In fact, it cannot do anything. There are, and I'm not talking about like a computer could never truly love or something like that. This is not what I mean. I mean, actually, there are specific mathematical problems that are beyond the capabilities of a universal computing machine. And this is interesting to me. This is very interesting. The fact that it's not everything. There are certain, and I don't mean like some kind of nonsense problems. I mean real specific mathematical problems which cannot be solved by any algorithm, by any universal machine. I would say this is interesting, but I find this very deep philosophically. I don't know if you've ever thought about this kind of a thing, but in my opinion, this is deep because if you think about Really, like I said all along, I'm not talking about the capabilities of any specific computer, like this iPad or that computer there. I'm talking about any kind of physical computing device that you could build. It will have limitations like this. Why I say this is deep, in a way that I find this very interesting, in a way that's a little deeper than, a little more personal than other like math classes that I teach. Because it makes me think about the human brain, right? The human brain is a physical object. It exists, as a physical object, and it is something like a universal machine. It can do things. It's like electrochemical or something. It's a biological thing. But let me just say, if the human mind is, I will say only in quotes, a physical object, because the human brain is a physical object. I believe that. Now, some people say, well, a person is like a physical thing, but also a person has an eternal soul, which somehow lives inside your brain or something like that. And I don't mean to demean this point of view. I personally do believe in the eternal soul. But I also believe that the human brain is a physical object that really exists in the real world. And if that's true, then the human brain is subject to the same limitations of any other physical computing device. All right? If the human mind is only a physical object, I think the word only is doing a lot of work. It is a physical object, but extremely complex. The human brain is. Anyway, we human beings have the same limitations as any computing machine. And you can look at this two ways. To me, what it means is that there are certain kinds of things which a human mind is not capable of processing the answer to, all right? Because there are certain questions that universal computing machines cannot answer. That's interesting to me. It's also interesting the other way around. It also means any of the things which I imagine to be special capabilities of a human mind, those capabilities in theory can also exist in a physical machine, right? In a computer, right? I think if you think about it a little bit, you have to, at some level, I think you have to agree that in theory, you could make a simulation of a human brain inside a physical computing instrument, a computer, and then it would be able to do all the same stuff that a human being can do. So anyway, what I'm trying to say is, now you don't have to agree with me about any of this kind of philosophical eternal soul or whatever, but I hope that you can all agree that this is definitely some deep stuff, in the sense that whatever we are saying about the large-scale theoretical capabilities and limitations of computing instruments in the real world, all of those things, in some sense, apply to us, ourselves, as well. And that, to me, is really is very interesting. We'll talk more about this later on in the course. I think that's all I had to say by way of introduction. Anybody got any questions, any thoughts? I, myself, am an expert in the mathematics. From time to time, I like to talk about sort of deep thoughts about the nature of human reality or something like that. I'm not an expert about that. So I hope that you feel free to disagree with me about any kind of philosophical mumbo-jumbo that I mention. My intention by mentioning this philosophical mumbo-jumbo is not to make you agree with me, but I hope that you will find these things interesting to think about. So agree with me or not, that's fine. I hope that you agree, these are interesting questions that are raised by this whole field of knowledge. All right? Great. We got 6 minutes remaining. That's all. That was my whole introduction here. I don't know if it's worth getting into the details with only 6 minutes remaining. How about? Oh, now it's only 5. Let's just call it a day at that. We'll start with the real technical stuff next time. All right. Please let me know if you have questions. I'll hang around for